All right, hello there. So today we're going to talk about the CPU, our central processing unit. Okay. Um, in kind of crude terms, it's the brains of the computer. Crude terms now. Okay. So what does it do? It processes the data and the instructions on what to do with that data. It's as simple as that. That's what it does. Okay. The power of the CPU to do this, its computational power, is determined by a number of factors. Okay, and we will talk about all of them. Okay, but just to name them, just so you know them: clock speed, cores, threads, and cache. Okay, size. Now we're not going to talk about them today. We'll talk about them when we're talking about what affects the CPU in terms of, and we'll talk about that further down along when we've got a bit more of the kind of pieces of the puzzle together. Okay, but just so you know that the CPU isn't this all powerful thing. It is determined by a number of factors that feed into it. Okay. There are two types of architecture that are commonly associated with CPU. One is called the Harvard model, and the other one is called the von Neumann or Neumann, depending on how you say it, model. Okay, after John von Neumann, and I've talked about him a good few times. He's one of my heroes, if you want to, for want of a better word. So von Neumann is the man that we're going to talk about. He's the man that's on the course. I have talked to you in class about the Harvard model briefly, but the von Neumann model is the one that is used. It's the de rigueur one. Okay, it's the one that everyone kind of uses. So that's the one we're going to talk about, and we'll see how we go with it. Okay, so let's have a look at what the CPU actually contains. Okay, there's three basic areas within the CPU. Okay, we have the control unit. I'm just going to call that the CU from now on. Okay, then we have the arithmetic logic unit. The ALU. Okay, and finally, we have the caches. Not Johnny Cash and his wife, but close enough. Okay, so we'll briefly talk about them, then we'll actually go into the nitty-gritty and see how these actually work together to do what we need it to do in terms of the computer. Okay, suppose that's the kind of the end of this kind of cycle. This is what we're trying to get to. So let's have a think about it. The control unit is an overall control. Of the CPU. Okay, it executes programs by following, and this is very important, and we'll talk about this, the fetch, decode, execute cycle. That is so important, the fetch, decode, execute cycle. That does come up quite a lot throughout the Leave Insert course. This is where you start learning about it and start understanding it. Okay, so it controls the flow of data throughout CPU and also coming in and out of the CPU. Okay, so it controls the data that goes to the ALU and the caches, but it also controls the data that comes in from memory and that goes out to input output devices. All, you know, it does all that as well as the internal controls. Okay. The ALU, what does it do? It does all the calculations. So it does your add, subtract, multiply, divide. It also does your and, not, or, etc. Does all your booleans. Okay. It also contains the accumulator. Okay, which is a type of register which we will talk about. And it's an important register. Okay, and it does exactly what it says on the tin. It accumulates something. You know what? Accumulates something. Okay. Cache is very fast memory in the CPU. Very fast memory. Slower than registers, which we talk about, but faster than RAM, which we will talk about again in another group. Okay. They're very, very expensive. Okay. Very, very expensive. There's 3 types, L1, L2, and L3. The L1 is the best, but the most expensive. Okay. But it can hold the least amount. Okay. So just think about that. L1 is the most expensive cache, the best cache, but it holds the least amount of information. L3 is the cheapest. It holds the most, but you know, it's the slowest. Okay. They're still faster than RAM. L3 is still faster than RAM, but it's not as good as L2, and L2 is not good as L1. So, you know, there's levels of cache that you can have. Okay. Obviously, the CPU also contains registers. Okay. Now, they are super duper fast memory, but they only hold tiny, tiny pieces, literally one piece of information instruction at a time. Okay. That's why they're so fast. They're basically just read write. Okay. That's all they are. Much quicker than any other form of memory. So that's your kind of overview of it. Now we're going to go into detail on it now, but just so you've got your kind of idea in your head of what we're dealing with. Okay, so just very quickly before we go into the kind of the big detail. CPU, central processing unit. It processes all the data and instructions. The power of the CPU is determined by clock speed, the number of cores, the number of threads, and the cache size. There's 2 types of architecture that are designed around CPUs. One is the Harvard architecture, which we don't do, but which we have talked about briefly in class, and von Neumann, after John von Neumann, and that's the one that most computers now run on. Okay. There are 4 main kind of sections in a CPU. The control unit. It's the overall control that executes programming following the fetch, decode, execute cycle, and it controls flow of data both within the CPU and in and out of the CPU. The arithmetic logic unit, the ALU, does all the calculations, all the basics, and all the Boolean. It also contains a register called the accumulator, which we'll talk about in a minute. The caches are very fast memory in the CPU. They're slower than registers, but they're faster than RAM. They're very, very expensive. There's different types of them, L1 being the fastest, but holds the least amount and is the most expensive. And you get the idea, the opposite at the L3 stage. And then you have lots of registers in there. And they're basically read-write. They do one thing only. They capture input, output within the CPU and just pass it on. They're super duper. They're ridiculously fast, but they can only hold a minuscule piece of information at a time. So there's your basics, and I mean basics. Now, von Neumann architecture, because this is probably where it all leads to. Von Neumann came up with his design in 1945 and still describes how 99% of all the computers in the world still work today. Okay, that's how nifty it is. So I'm going to try and visualize it in one fell swoop. Okay, so imagine this is our pared down CPU. Okay, here's your output, and here's your input, and here's your memory. Memory could be primary or secondary storage, doesn't matter, it's just memory. Okay, so within the CPU, we have 4 areas. We have the CU, okay, we have the ALU, and then we have the registers. Now, you don't have to do this visually. If you're asked to talk about it, you don't have to do it visually, but I've learned it visually because it makes it easier for me to, once I know the picture of it, I know what's the site, what's the kind of the flow, for want of a better words, of all the information. So when I was learning this off, first of all, what I did was I learned off which way the arrows go. So I straight away know that an output arrow has to leave, an input arrow has to go in, the memory goes both ways. And then within the CPU, how do the arrows work? Okay, well, the arrows work both ways. That's important. That's the trick here. You can remember that in the CPU, everything talks to everything else. The C control unit talks to the registers. The registers talk to the control unit. The ALU to CU, the CU to the ALU to the registers to the ALU. They all talk to each other. Okay, so now once you've got that done, then it's just a bit about remembering, well, what's inside the control unit. Okay, inside the control unit, you have what's called the program counter. Okay, inside in the ALU, you have what's called the accumulator. Okay. Inside in the registers, you only have to know 2 of the registers in the registers. What's called the MAR, the memory address unit. Okay. And the memory address register. It was control unit. Memory data register. That's all you need to know. So now I'm going to talk about each one of them, and then I'm going to explain the cycle to you. Okay? So, try and get a program counter. That's PC. Okay? So what does the program counter does? It holds the memory address of the instructions for each cycle that it has to do something. Okay, simple as that. It holds the instructions. Okay, so it's a list of instructions in there, and it says, you know, each instruction has an address. Okay, that's all it has in there. The memory address unit. Okay, the MAR, memory address unit. Okay, holds the memory address. Okay, holds memory address for what a CPU will use. for example, data or an instruction. Okay, the MDR holds the actual data or instruction. So the MAR holds the address of where it is. The MDR is where it is. So for example, it'll imagine that's the phone book. Oh God, you don't know what a phone book is, do you? Okay, imagine that's the index at the back of a book that lists each page that you're of whatever word you're looking for, and that's the page when you go to it with the word. Okay, so if that's like, giraffe is on page 42, the MDR holds page 42, but that holds the instruction to go to page 42. So there's the subtle difference between those two. Okay. Then the accumulator. This side, the accumulator. Accumulator. The accumulator holds the results of calculations performed by the ALU. Okay, so it holds like a rolling total, it keeps it going. Okay, and the cycle continues. Okay, now I'm going to try and one of the beauties of the von Neumann system, and I don't know if you can see it, is that it only uses one memory for both the data and the instructions. They're not stored in two different memories. Okay, so that increases efficiency, for want of a better word. Okay, so you can imagine you load a program into the system, into the program counter. Program counter holds the memory address of the instructions for each cycle. So step one. So in step one, it'll say go and find in the memory address register, step one. And you find step one. It says step one, go to, page 42. You go to page 42, you get what's in page 42, you put it in here. It does something with it. It stores it. And go to step two, find step two. Step two is on page whatever, find it on whatever, pop it in, do something to it, go to step three. And you get to see this fetch, decode, execute. Okay? Fetch, decode, execute. Fetch, decode, execute. Fetch, decode, execute. And the number is consistently going up. There could be 1 million steps in that counter to perform that operation as it comes in from the program, as it's loaded into the CPU. But each cycle is called one thread. Okay? And obviously, this represents one core. So 2 cores, 2 threads, 2 operations per cycle. You get the idea? 4 cores, that means you're doubling, you're 4 times with this one. 8 cores, 16 cores, 32 cores. You get the idea. The more cores, the more times this thing can happen in a given second. Okay, so that's the beauty. Essentially, all CPU does is carries out instructions one after the other billions of times a second. So the fetch, decode, execute cycle describes this. Okay, so you copy the memory address from the program counter to the MAR. Okay, copy the instruction stored in the MAR to the MDR. That increments so from 1 to 2. Okay, to start the next cycle. Decode it. Inside the MDR, it's decoded by this the control unit. It prepares for the next style, but it might load a new one. Then in the accumulator, the calculation is done and done. That's it. That is literally what it does. Okay. It is a tough ask to kind of understand this in one go. Okay, so you're probably wondering, well, what's the difference really between the MAR and the MDR? Okay, well, if you start the cycle in your own head, step one, okay, step one says whatever, go to instruction one, and instruction one is in here, and instruction one says find the word giraffe. Okay, so you find giraffe, you go and you find giraffe, and it's on page 42. Okay, and on page 42 it says giraffe tells you to eat leaves. So that's the instruction you're going to send here. It'll eat the leaves, and then it's already incremented it to number 2. Once that's sent, it increments the next one. So now step 2, find instruction 2. Okay, you look up instruction 2, and instruction 2 says find rhino. So you send rhino down here, and rhino is down here, and you get the cycle just keeps going on. So, you know, the address, the memory address from the program counter goes to the MAR. Okay, the MAR finds where that instruction is, sends it here, which looks up that instruction, sends it to here, which follows out that instruction. It does what it says on the tin. Okay, the cycle keeps continuing, and this accumulator can build up a couple of things before it finally sends the last piece of information here. So when you get to the end point, the accumulator then could just release, whatever you want it to release, depending on, what you're asking it to do. So that's the basics of it. That's the von Neumann architecture. It's a tough one. What you need to know for the leave insert: program counter, memory address register, memory data register, accumulator, ALU, CLU registers, the cache. Okay, where is the cache? The cache is everywhere, but mainly your cache tends to be in your ALU. And the idea of cache in your ALU is, let's say you're performing a number of tasks repetitively in a particular program. It can store that particular task. For example, let's say it's multiplying by the number 5. So this is some type of thing that multiplies by 5 a lot. So rather than have to keep looking for new instructions to multiply by 5, it stores that instructions there for quick access. So you don't have to find the algorithm to add a 5 onto a number. It's stored in there temporarily and allows you to go quicker at it. So that's the example of where cache would come into play there. Okay, thank you very much. Goodbye.